Magnitude and direction of 2D vectors. So we've spoken about the magnitude being the length of a vector, and here we're going to look at an example of how we can find that magnitude. We have our xy axis. We have a vector with x component of 3 and y component of 4. Let's call that vector u. So its column matrix will be 3, 4. Might be able to see that its magnitude can be found with just simple Pythagoras, because we know this distance is 3 and this distance is 4. And the way we're going to write magnitude is actually with an absolute value sign. Looks like an absolute value sign. So this is our magnitude. So if you see this is asking for the magnitude of u, which is asking just for the length of the vector. And it should be pretty easy. We can find that length by just doing the square root of 3 squared plus 4 squared, which is going to give us root 9 plus 16, which is root 25, which is just 5. And that's how we can calculate the magnitude of any vector. So let's try and make it a little bit trickier. Let's try xy axis. And this time let's give two vectors. Let's go vector A with column matrix 6, 3, which means going across 6 and up 3. Let's go vector B. With column matrix 2, 6. It's gone across 2 and up 6. And we want to find the magnitude of this vector here, v. So we're asked to find the magnitude of v. Now the first thing we need to do is get an expression for v. And when the vector's drawn across the two arrowheads, you know it's either going to be b minus a or a minus b, depending on which way this vector v is pointing. And sometimes it can be confusing. So just to take the confusion out, one way to do it is to start labeling the points. So if we call this point O, this point A, and this point B, we can write something that will hopefully help us out. So what we want to realize is that the vector from O to A, and then looking at the vector from A to B, is the same as just going from O to B. So O to A, then A to B is the exact same as O to B. So we can write that the vector O to B is exactly the same as going from O to A, then A to B. And that vector A to B is the one we're really interested in. So let's just make that the subject. And we get the vector, get rid of that. Then we get the vector A to B. We just minus vector OA from both sides, and we get vector OB minus vector OA. So that's AB. A to B is just the vector V. O to B is the vector B, and OA is the vector A. So we can see the vector V is just B minus A. So that'll take the confusion out if you can't remember whether it's B minus A or A minus B. And we know when you're subtracting vectors, all you need to do is minus the components. So that vector V will just be the component of B, which is 2, 6, minus the components of A, which is 6, 3. And then we get 2 minus 6 is minus 4, and 6 minus 3 is 3. And this is the components of V. So it should be easy to find the magnitude of V now. It's just going to be the square root of minus 4 squared plus 3 squared. and that's just going to give you 25. Square root of 25, which is 5. So let's talk about direction of a vector. Now, direction of a vector is similar to trigonometry in terms of when measuring the angle. So let's look at a vector with components 2, 2. And so direction's measured with an angle from the positive x-axis. So in this case, we have our angle theta. We're measuring from the positive x-axis, which is this side here, until we get to the vector. So this angle here is going to tell us the direction of this here. And again, you might be able to see that it's just going to be simple trigonometry. The fact that we know this length is 2 because its y component is 2, and this length is 2 in the triangle because its x component is 2. So we can easily write an expression for the direction saying that tan theta is just going to be 2 over 2 in this case here. So you get tan theta equaling 1, and then doing the inverse tan of both sides, we're going to get theta equals 45 degrees. And we can generalize this a little bit, saying if we have some vector A with components AB, the theta determining its direction is just going to be the inverse tan of B over A. Let's have a look at an example of finding the direction of a vector. Let's look at its xy axis and taking a vector with column matrix 3, 4 and another one with -2, 1. And we are after the direction of this vector here. So let's call this vector A and this vector B, and we're after this vector V. Again, let's just make things a little bit easier. We'll call this point A, this point B, and this point O. And looking at resultant vectors, go from O to A, then A to B is the same thing as going from O to B. So we're able to write out that going from O to B is the same thing as going from O to A, then A to B. And rearranging, making A to B the subject, we can see that we get O to B minus O to A, and that's just vector V is just going to be vector B minus vector A. And to get the components of vector V, we're going to take the components of vector B and minus the components of vector A, which is going to give us -2 minus 3 minus 5. 1 minus 4 is going to be -3. This is the components of V. We know if we want its direction, we can get an angle theta, where it's going to be inverse tan of its y component over the x component. And that's going to give us 31 degrees. But we have to realize that that angle 31 degrees is not a true representation of its direction because it has to be measured from the positive x-axis, and we can see its direction here, where you can imagine a horizontal line, and that 31 degrees is actually this angle here. So all we need to do is add 180 degrees to our answer, and that's going to give us 211 degrees as our final answer.